Hi everybody, and welcome to our discussion here of Module 2, which is getting into our discussion of maps and geographic techniques. And so in this section I'm going to talk a little bit about four big points that are some of the, I guess, more major points that are in this module. This is not the only material you're responsible for in this module. There's the book reading, there's some of the videos that are linked, as well as some of the other things that are in the PowerPoint, which really just kind of correlates to what's in the book. But there's a few things that I want to make sure that I have a chance to explain verbally, because sometimes just looking at it in the book I think isn't quite enough. So the four big points we're going to hit today are, first, just talking about what maps are in general, talking about map projections and the way that they distort. And basically the idea that any flat map you're looking at, whether it's on paper or whether it's on a screen, is actually not terribly accurate at certain scales. And then connected to that, we will talk about the concept of scale, which is very important in geography. There's a couple big definitions there. And then the last thing I'll talk about here under the four big points are some of the what are called geotechniques, or things that geographers use. Geographic information systems, which is essentially like computerized mapping, but a little bit more, as I'll discuss. And also GPS, or global positioning systems, which most people use on a fairly daily basis, whether it's getting directions off of your phone, or looking at things like Google Maps, that kind of stuff. And we'll talk a little bit about how those work. And that's really important because geographic information systems and things like that, and GPS, are places that are really important for people getting jobs that have backgrounds in geography. I have a student who graduated from some of my classes just a couple years ago who's now working for Apple Maps. She used to work for Google Maps, and she got her degree in geography, had some basic background in mapping skills, and has got into a couple different jobs now. She lives out in California working for Apple and loves what she does. So it's a really important aspect of when people study geography, because there's a lot of jobs there. Okay, so let's go ahead and hit these major points. The first one is just the definition of a map, which is, as shown here, a reduction, simplification, and abstraction of some part of the Earth. And so what does that mean? Well, let's take a look at the three terms there separately. A reduction. Well, a map is smaller than the place that it is usually portraying. Otherwise, it wouldn't be much use. I mean, no sense having a map of New Hampshire that is the size of New Hampshire, right? You want a map of the state that can actually, fit on your screen or fit in your pocket if it's on paper. A map is also a simplification of some part of the Earth. It doesn't have everything that exists in that area shown on that map, just the things that you're interested in. So if it's a road map, it shows you the roads and maybe where the cities are. It doesn't show you every tree, every church, every house, every school, just the stuff you need. It might show you things, even if you're looking at something like something on Google Maps or Apple Maps, where it might show you certain restaurants or other points of interest, but that's still a simplification. It's leaving stuff out. It's leaving out information. And that's very important, because that's how you determine kind of what your map is about, is what it is you emphasize and what things you're not. The last term, abstraction. Abstraction means that it uses symbols to portray what's actually there. In other words, if the map does have a picture, wants to show you where a church or a restaurant is, it doesn't actually show you a real picture of it as much as it shows you a symbol. Like for a restaurant, it might show you a little fork and knife, or it might show you a cross for a church, that sort of thing. And so because of that, it uses abstract symbols. And so that's where we get this definition of a reduction, simplification, and abstraction of some part of the Earth. Okay. And so maps are, of course, a very important tool of geography. Maps are the primary tools that we use to analyze information spatially. And the art, science, and technology of making maps, sorry, it says of making maps behind me here, but it might be hard to see, is referred to as cartography. So as you'll see in the book and in the PowerPoints and in my discussion, when we talk about cartography, or what a cartographer is, that has to do with making maps, right? Cartography is the art of making maps. Okay, so that gives you an idea of kind of what we're talking about when we talk about cartography. All right, so the other key point that I want to discuss is the idea that that we need to talk about is map projections. All right, okay. So, anywho, My apologies. I keep getting interrupted by a small child. Anyhow, so the key point number 2 here is about map projections. And one of the strange things about map projections is that anytime you take a round, circular, spherical surface like the Earth and smash it out onto a flat surface, it makes distortions. Really, the only way in which the Earth can actually be represented accurately is on a globe. However, it's hard to carry globes around in our pockets, right? We usually want to see it on a flat either piece of paper or a flat screen. And because of this, we have what are called map projections. Now, a map projection here, as it says, is a method of representing the curved surface of the Earth on a flat map. And the most important thing to remember here is that all flat maps distort some or all of the 4 main properties of the actual Earth's surface relationships, which are area, shape, distance, and direction. Think of it this way, where it says here, think about an orange skin. If you take an orange, a round spherical orange, and you drew things all over it, and then you took that orange, pulled it apart, and then tried to smash it out flat, the things you had drawn on it would start getting distorted, right? Well, that's what happens when people make maps of the Earth. And so it's something that most people don't necessarily appreciate, but the fact of the matter is that every map is doing this. And so we have to be conscious of it. And so when map makers make a map, they usually try to have one of these things distorted or a couple of these things distorted to keep something accurate. And so, for instance, some maps are what they call equal area projections. And what they do is they maintain that, so let's say of the entire world, we have a map of the continents of the world. A equal area map will make sure that all the continents are their actual correct relative size to each other. But when you do that, it actually makes their shapes really distorted. There's another thing you could do, which are called conformal projections, where the shapes are accurately portrayed, at least in certain areas, but then things like the area is distorted. And typically, a lot of maps that we're used to seeing in the world distort actually area. They're not equal area. So it says here, a map cannot be both equivalent and conformal. So this gives this example, and this is from the textbook, where it shows that, depending on how you do the projection, what kind of thing is going to be distorted, and it gives you this example by using like what somebody's face would look like if you ended up kind of using these projections. And so one of the projections that a lot of people are used to seeing is this one down here, which is a Mercator projection. And so one of the things about this projection is that everything actually has the correct shapes. Africa is actually shaped like that. North America is shaped like that. Asia is shaped like this. However, when you get towards the poles, it drastically overestimates or kind of overrepresents how big those areas are. So, for example, Antarctica looks gigantic, which it isn't. Greenland looks much, much bigger than, say, Mexico. But Mexico, in reality, is actually much larger than Greenland. So instead, what you'd try and do, if you want to, but one of the reasons why this kind of projection is used is because the shapes are accurate and also because directions are somewhat accurate on this kind of map too. But it gives people the false impression that Europe and North America and Asia are kind of bigger than they actually are. If you looked at this map, you wouldn't know that Africa is actually bigger than all of North America. So what some people started doing then is making what are called equal area projections, and this is an equal area projection, where it shows that Africa actually is this large, which is much larger than North America, much larger than South America. The problem with this map is that things get really distorted in terms of their shape. So North America is not shaped like this. It's sort of taking those upper areas and smashing them down. So you have to kind of recognize when you're looking at different types of maps that something is always distorted. Another way that map makers will choose to kind of do their distortions is there's something called equidistant projections, where you take one place on the Earth and you put that sort of in the center of your map, and all the distances from that particular place are accurate. That's not true of distances between other places, but at least from that one central point. So in other words, you can make a map of the world with Keene, New Hampshire, as the center of the map and show all the places and show exactly how far away they all are from Keene, but it would be a very weird sort of smashed out map. So let's see, I've got an example here. I'll come back to this. This would be an example of one of those from the North Pole. So all the distances from the North Pole here would be accurate, but it wouldn't be accurate if you tried to measure the distance, say, from over here in Somalia all the way to Miami or something. That would not be accurate. Then there's another projection called the Robinson projection, which is a example where this actually doesn't have anything completely correct, but it tries to have everything not too distorted. So the shapes aren't exactly correct, but they're better. The sizes aren't, none of them are completely correct, but it's kind of a compromise between all these different distortions. And something I had here on the previous slide, one of them is showing this idea of the Robinson projection, which is the one that is a compromise between equal area and conformal. It doesn't show true distances or directions, but it just kind of tries to be a good compromise. There's also the azimuthal projection, which directions are true all from one central point, but not necessarily true in other areas. So you'll see different maps that kind of take these different views. Okay. So, key point number 3, talking about scale. Okay, so there's 2 definitions here that you have to really know about scale because they're both very important to geographers. The first is this general thing when we talk about the scale at which something happens in the world. So the definition here is the spatial extent over which something occurs. People will often say, oh, that's a process going on at the local scale, or that's a global issue, right? They'll talk about things like the emissions from a factory are making air quality bad in the city next to it. And they'll say, okay, that's a local scale phenomenon. But if they're also talking about, say, the factory putting out carbon dioxide and the effects that might have on global warming, we'd say that's a global scale kind of impact. And so geographers like to talk a little bit about what scales people are using. Okay, so that definition of scale is one of the important ones here in terms of what is the spatial extent over which something occurs. There's a second way that geographers talk about scale, and it has to do more directly with mapping, and that is the ratio between the measurement of something on a map and the corresponding measurement on the Earth. And so, in other words, sometimes on a map you'll see something like, usually a little scale bar, like even on your phone it shows a map. It might show you kind of how far a mile is. So you're like, oh, if it's this big on my phone, then that means it's actually a mile in the real world. And then as you change the scale, right, by zooming in or zooming out, that scale will change. And then all of a sudden an inch on your phone might be 10 miles or 100 miles if you're kind of zooming out from something, right? Or if you zoom really, really close in, that same inch on your phone might be, as much as only like, 100 or 200 feet in the real world. And so when people talk about scale in terms of mapping, that comes up. And so they're really represented in 3 ways: verbal scale, graphic scale, and also what's called a representative fraction. Verbal scale is kind of what I was just talking about when you say 1 inch equals 100 miles. Or a graphic scale, let's see if I think I've got one here. Let me see here. Here's a graphic scale. That's often you'll have something like this that actually kind of shows you, okay, this distance here, from here to here equals 50 miles, or from here to here equals 60 kilometers, that kind of stuff. And then again, verbal scale up here, 1 inch equals this many miles. The other representative fraction scale is where you'll see something like this, 1 to 62,500, right, 62,500. And that means that 1 of anything on the map, or your phone, or whatever you're looking at that's a map, equals that many of those same units in the real world. So what that means is that 1 inch on your phone is 62,500 inches in the real world. It's also true that 1 centimeter would equal 62,500 centimeters in the real world. So, but it's done as a representative fraction. Okay, and so one of the things that can be very confusing for people new to geography is that people talk about about small scale and large scale, and these are a little bit weird when we talk about maps because of the way that representative fraction works. Think of fractions. The larger the number on the bottom, right, the smaller the number is, right? In other words, 1 over 10, or 1/10, is bigger than 1 over a million, 1/millionth. So because of this, a large scale map, what geographers call a large scale map, is actually something that is showing you a close-up of a small area. So in other words, it says here, ratio of map distance to ground distance is relatively large, but it's considerable detail. A ratio of 1 to 50,000 or less. Again, remember, a fraction that has a smaller denominator, right? So if it was 1 to 10, that would be showing you an even smaller area, but with much more detail. So in other words, to make a long story short, a neighborhood is a large-scale map. the same size map showing the world would be a small scale map. And sometimes that's the opposite of what people might usually think. So for instance, these are different scale maps of the Boston area, right? Charles River, all of that. And you can see here that 1 to 25,000 is the large scale, where it's really showing here most of like the downtown area. Then you get to 1 to 100,000, right? And it's kind of showing you a little bit more. So that's a smaller scale map, even though it's showing you more territory, right? And then you can go all the way out here to 1 million, and you can see that it's showing you like all of the North Shore and South Shore area out towards Cape Cod, all of that kind of stuff. And so as you're going out, that's actually a smaller scale map than the one showing you just downtown. Okay. All right, so key point number 4. The fourth point is how important contemporary spatial technologies are in geography. And I'm just going to focus on 2, global positioning systems and geographic information systems, which a lot of people just call GIS. Okay. And these are important, again, as I mentioned, partially because there's just a lot of jobs that these are, that require these things. The other kind of important technology, which is in the book and also in the PowerPoint, is remote sensing, which is sort of like satellite imagery, that kind of thing, which is another thing that geographers use. But I'm just going to focus on these 2 here, and then you can see in the PowerPoint and the book some of the stuff on remote sensing. All right, so I'm going to start here with GPS. And most people know how to use GPS. They know that it's something that's already embedded on most of their phones and that kind of thing. But not a lot of people understand exactly how this thing functions. And so to do this, there's actually a network of satellites up around the entire Earth that essentially give perfect coverage around the entire Earth, so that no matter where you are, there's always at least 4 satellites directly overhead. And so there's a lot of applications for this. They were, these satellites were first put up by the military, and the idea was so that they could use them to know exactly where things were for precision-guided weapons and for navigating, mapping, and that kind of stuff. But now it's also really important for commercial and non-military mapping. It's also really important for when you're doing environmental assessment, being able to see exactly what species exist where and being able to kind of geocode and tag where particular things are found, that kind of stuff. And of course, also giving people directions, knowing where to go, etc. So because GPS receivers have become so miniaturized, now they use them for tracking animals. Of course, they're in our cell phones, tracking criminals that are on probation, this kind of stuff. And as mentioned, there's this whole constellation of satellites up there that make this possible. This video, which is in the announcements, this link, and it's on the PowerPoint as well, you definitely have to watch this. It's something that gives you a good idea of exactly how that system works. And I think that video does a good job showing you. And also about the fact that there's now going to be a next generation that's more accurate of GPS satellites. Okay. So the other thing, too, is that, of course, going now into the section more on geographic information systems, computerized mapping has become more and more important. People who use Google Earth or, maps on their phones or computers know that, of course, that this technology is kind of expanding in terms of the way people use it all the time. And, both in terms of those kind of platforms like Google or Apple Maps, but also by using it in terms of mashups, where you take digital maps and merge it with data that you either put in yourself or get from other sources, right? More interactive mapping. And we'll see in our first assignment exercise for this class some of the examples of how people are using these kind of geographic information systems and this data that they're collecting that's got a spatial component to it, and how they're kind of making these different maps, whether it be political maps or maps of where jobs are or all that kind of stuff. All right, so kind of the way in which geographic information systems came about is essentially it was about computerizing mapping, which used to be done all on paper. But there's essentially 5 major components to this. Is that you have to be able to get data out there, that you have that we have the information about where it's from, right? So you have to take that data and input it into the geographic information system, which is essentially a computer program. It allows you to manage that data, to manipulate it and change it and shape it and add to it and all of that. And it also has very powerful tools for analyzing that data, looking at what the relationships are between different parts of data or different data points that you have, and then also making maps, right, the output from this. And the way essentially it works is by using what are called layers. And so what it does is it takes, it's as if you had paper maps that you're laying one on top of the other. And so you might have, like this example showing here, a base map that shows where the roads and all this sort of thing are. And then maybe you have voting precincts as another map. And you're essentially putting that down on top of the road maps that you have. And then maybe you also want to see how that correlates to where property lines are. You can take that map and put it on top. And then you can select things like, say, hey, show me all the spaces that are in the voting district number 7 that are close to a road that are privately owned. And then it'll just, boom, tell you exactly which ones those are. And so you can see why different companies really like this. There was, I don't remember how many years ago it was, but I remember seeing a job ad out there for someone to work for Red Lobster, the restaurant company. They wanted to hire somebody that could take all the demographics, see essentially where the people are that are typical customers of Red Lobster, not just the people that have been customers, but the kind of demographics based on income and race and education level, etc., that tend to like Red Lobster. Make these maps on where those people are, and then find the best places where they could potentially put Red Lobster restaurants, right? And so that's just, of course, a kind of mundane example, but that's the kind of thing that people do with GIS in terms of figuring out how to site businesses. And of course, there's other things too where people could look at it and say, okay, we want to make a protected area to protect a particular species. We need it to be within 100 yards of a river, so you'd have a river map, and then you'd say, okay, it has to be on publicly owned land, so you could see where the public land is that's within that distance of a river and all of that, and then figure out where to put your protected area. So GIS has a lot of applications. Biologists and ecologists use it for studying environmental problems. Epidemiologists, which are essentially people that study disease and disease outbreaks, use it a lot to study how diseases have diffused, where they're starting from, what factors seem to be at play, where the diseases are arising, that kind of stuff. Political scientists and people working with elections use this stuff all the time to try and figure out where voters are that might vote for them, where to more effectively campaign or to target different kinds of political ads and all that kind of stuff. Sociologists like to use it for examining different social patterns, such as, is there racial segregation in different parts of cities in the US? We'll actually look at some of that later in the semester. And then, as mentioned, private companies like to figure out where to put their businesses, analyze where they can do sales territories or optimal driving routes for how to deliver things to their different stores and where to put their warehouses and all of that. And governments use it a lot for transportation planning, also for looking at things like where do crimes occur, and is there things that they could do better to try and mitigate crime in those areas that are have higher levels of crime. And also it's very critical, these kinds of mapping programs, for figuring out how to respond to disasters after they occur. So one of the things you'll see in the discussion questions for this section is to kind of take a look at what sort of jobs are available out there close to where you live in GIS, because that's where a lot of people who go into geography do get jobs. Okay, so that's the end of the key points for this section. Please be sure to read the whole chapter, check out the rest of the PowerPoint, and watch the other video links for important info. One of the other video links for this is the one on Captain James Cook. He was a very early cartographer and explorer, and kind of some of his methods, and also the way in which kind of the art of mapping has been important historically. So that's it for this section. I'll see you at the next one. Thanks.